There's a kind of an algebraic story that goes with what I'm saying, but it's really the pictures that will dominate today. And probably a good place to start is with some elementary projective geometry, which is a very beautiful and lovely basic subject. So suppose that we start with, let's say, 4 points in the plane. Let's say 1, 2, 3, maybe 4. Okay, so there's our 4 points, and then we can do what we do in projective geometry, which is to join points with lines. And that's really all that we can do, as well as taking intersections of lines. So we have some lines. If we have just 3 points, then there's actually very little we can do. We can join those 3 points and create a triangle, but then in projective geometry, there's no more that we can do. So the subject really starts with 4 points, and the configuration I'm going to show you now is one of the perhaps 3 great configurations of projective geometry. The other one's going back to Pappus's theorem and Pascal's theorem, and also to Desargues. So here we have 4 points which form a quadrangle. So 4 points is a quadrangle in this subject. And this is actually a complete quadrangle in that we also see the 6 lines that they generate, and we get some new points. We get the intersections of these 6 lines. So let's there's one there. Oh, I see I've missed one. That's right. I missed a line. Where is my ruler gone? We need 6. There we go. Okay, so now we have these 3 new points. Those are called the diagonal points of the quadrangle. And of course, then they form 3 additional lines. And that triangle then, that is now in blue, is called the diagonal triangle of the quadrangle. Okay, and maybe I'll emphasize it by just coloring it in a little bit, although that doesn't really have any meaning in projective geometry, just so you can see it. So that's the diagonal triangle of the quadrangle. And now we can see a few more things that we didn't see before. We see some additional intersections between these new diagonal lines. So there's an intersection there, and one there, and one there. And I guess there's one here, and there's one here. There's often one sort of off the page somewhere. Yeah, so there'll also be one meet where these 2 meet, so it'll be down here somewhere, in that direction. Okay. And now the beautiful fact is that those 6 points that we've now found, maybe their colors are not so obvious, so maybe I'll mark them a little bit specially so they distinguish them from the red ones. These 6 points are not arbitrary points, but they are forming a very pleasant configuration. Namely, we can join those 3 points with a line, and we can join those 3 points with a line, and we can join those 3 points with a line. Of course, there's that one down there. And we can join those 3 points with a line, also joining with that one that's far down there. And so we move from the quadrangle to a triangle, a diagonal triangle, and now we see that we have 6 points and 4 lines. So we get 4 lines, which make a quadrilateral in the subject. And the situation is quite symmetrical between these things, so one can go in either direction. We could have started with the quadrilateral and gone the other way around and gotten a quadrangle. So this is a very interesting configuration of 4 original points, and then 3 more points, and then 6 more points. So a total of 13 points that we've created, and also a corresponding number of lines, 13 lines. So if you want to have a good example of where the number 13 comes up in mathematics, this is probably perhaps the best example. So this is really just the beginning. So there's a huge abyss now that looms ahead of us if we start saying, well, what else can we do starting from these 4 points? And in fact, you could spend the next 20, 30 years just studying the implications of delving further and further into what happens with these 4 points and successive constructions that you can make by doing further and further things. And this is, I think, a fascinating kind of a sign of the depth of projective geometry. Okay, so what we're going to be interested in is the relationship between this initial quadrangle and this triangle. And I want to observe that there's a relationship here that we can kind of say something about. We can say that this quadrangle is a standard, let's use that word, standard quadrangle for this triangle. Okay, so if we have a quadrangle whose lines all pass, or whose diagonal triangle is a given triangle, we'll say that this is a standard quadrangle for the original triangle. And this diagram actually shows you how to construct such. So if you started with the triangle, and let's say you started with one of the points, let's say one of the red ones, let's say we started with that one, okay, then you could sort of go backwards and you could construct this line here, and you could construct this line, you can construct this line here, and then you could find these points here. You could construct this one here, and you construct this one, so you get these points. And once you have these points, then you can construct these lines. This line here, and then this line here, and this line here, and this line here. And you've got. So we started with this one. When we created these other lines, maybe I should color them. Started with this one, and we've created that line, let's say. We've created this line, we've created this line. These red symbolizing these new things. And then we can join these ones. So, well, we already have that one. No, we haven't had that one yet. So we can construct these ones here. Because that's on the line, on the blue line and on the black line. That's on a blue line and on a new black line. So we can construct these orange fellows, and then we can construct the red ones correspondingly, because now we have lines and lines. Okay. So basically, by using the same configuration, we can start with an arbitrary point and generate a quadrangle, like basically the initial quadrangle, which has that triangle as its diagonal triangle. And we will call that relationship being a standard quadrangle for the given triangle. Okay, so that's first thing. I want to now talk about 5 points. So if we have 5 points, or 5 objects really, there's a certain kind of combinatorial game I want to play. So let's start with 5 points, and let's call them 0, 1, 2, 3, and 4. Of course, we can construct a pentagon. That's a favorite 5-fold object, and the number 5 is going to play a big role in today's talk. Okay, so that's a nice configuration. It's sort of essentially an ordering of the points, a kind of a cyclic ordering. Or in fact, we could actually think of it as being a dihedral ordering. So let's introduce the idea of a dihedral ordering of the 5 points. And they're really just 5 objects. They don't have to be points. And so we'll say that the ordering 0, 1, 2, 3, 4 is the same or equivalent to the cyclic rotation. So we're allowed to cyclically rotate. Whoop. But we'll also agree that we're allowed to reflect, go backwards. So if we read this backwards, we get 0, 4, 3, 2, 1, which is same as 4, 3, 2, 1, 0, and so on. So we'll call that a dihedral ordering. Okay? There's obviously 10 such permutations in such a dihedral ordering. And so the total number of dihedral orderings is going to be the total number of permutations, 5 factorial divided by 10. So there's going to be 12 of these. 12 dihedral orderings, and I want to show you them now. So I have to save myself a little bit of work. So here is a, that stays up there, might be a bit windy, let's see. Okay, so these are the 12 dihedral orderings of 5 objects. And you can see that I have introduced a bit of a graph structure. Maybe I'll put it over here instead. We've introduced a bit of a graph structure. How have we done that? Well, we'll say that 2 orderings are adjacent if they differ by a transposition. So 0, 1, 4, 3, 2 is adjacent to 0, 1, 3, 4, 2 because I've just swapped the 3 and the 4. Okay, so but remember, you should really think about these things as being forming a kind of a loop. So it's like going back to the beginning. So those things are adjacent, and that gives us a graph. Okay, and I've also given these 12 things some names: A, B, C, D, E, and F, and also sort of their bars. So I have to talk about the opposite. There's also a symmetry in this graph, which is the opposite, a kind of a reflection, and that's the standard construction of getting a pentagram from a pentagon. Okay, 5-fold symmetry. People have always been interested in pentagons and pentagrams. So if you start off with this ordering, then you can create this secondary ordering by going to every second one. So the pentagonal one, or the opposite one, is 0, 2, 4, 1, 3. Okay, so this ordering was called, actually it does have a name. Let's see what its name is. 0, 1, 2, 3, 4. There it is, it's F, so that would be the ordering F. Then this is the ordering F bar, 0, 2, 4, 1, 3. Okay, so there's a symmetry in this graph. Now, why should it be called a twisted icosahedron? Let's do some counting. First of all, this thing has 12 vertices, and it has how many edges? 30 edges, that's right. There's sort of 9 up at this level, and 9 at this level, and 12 in between. So we get 30 edges. And what about faces? Well, that's not so obvious because we haven't really defined what a face is. But I've given you a little bit of an indication as to what one might consider a face by sort of shading this top and the bottom parts. These are these hexagons. And if we look at this hexagon for a second, this hexagon is characterized by all of the vertices having 0, 1 somewhere as an adjacent pair. And this opposite vertex, opposite sort of face, is characterized by having 0, 1 as not adjacent. So if we agree that those kinds of subsets are some kind of generalized faces, then how many of them are there? Well, I've said it only depends on choosing 0 and 1. So there's 5 choose 2 ways of choosing a pair. So that's 10 ways, and there's 10 here and 10 there. So there's altogether 20 such faces. But they're not faces in the usual kind of surface kind of sense, but perhaps more in a... It's not a planar graph, yes. It's a simplicial complex, perhaps, in that kind of context. But nevertheless, these are the same numbers that appear in perhaps many people's favorite, or one of the favorite Platonic solids. This is the icosahedron, which has also 12 vertices and 30 edges and 20 legitimate faces. So there's perhaps some symmetry between this thing here and this thing here. Maybe not such a surprise because we know that the number 5 is somehow intimately connected with the nature of the dodecahedron and the icosahedron. Okay, great. So now I want to talk a little bit more about fiveness in the context of points in the plane. So the crucial fact about 5 points in projective geometry is that 5 points determine a conic. Okay, this is a beautiful fact. And 5 points in general position determine a conic. And let me say a little bit about that because it's kind of an interesting thing that figures actually in practice quite a lot. You have 5 points and you want to draw a conic through them. How do you go about doing that? So the standard approach is to take 4 points and consider the pencil of conics that go through 4 points. So if you have 4 points, then there's a whole pencil of conics. This is only one of them. There's a whole family, a one-parameter family of conics, including hyperbolas, of course, that pass through 4 given points. Now, included in that pencil are 3 special conics, which are the products of lines. So this is also a conic. That pair of lines is a conic, a kind of a degenerate one. And of course, there's then also this other one here, corresponding to the other diagonal point. And then there's the other one, other conic comparing for the other pair of diagonal points. So if we call one of these pairs, say, L1 and L2, and the other one, say, M1, M2, then these particular conics are just the products L1, L2. That's just the equation of the lines multiplied together. And then if you look at a combination like lambda L1, L2 plus lambda times M1, M2, say, equals 0, that will be a quadratic equation, therefore defining a conic, which necessarily passes through the 4 points, because L1, L2, and M1, M2 pass through the 4 points by arranging it that way. And so no matter what lambda is, that gives you a general point in this pencil. And so if you want this conic to pass through a 5th point, you just have to plug in the values of the 5th point in here and solve this single linear equation for lambda. Okay, single linear equation for lambda, and once you solve that, then you have the equation of the conic immediately. That's a much more efficient way of doing it than solving 6 equations and 6 unknowns. Now, the other important thing that we need to know about the conic through 5 points actually comes from Pascal's theorem. So let me remind you about that. So Pascal's theorem is an extension of Pappus's theorem. So if you have 6 points, say A1, A2, A3, and say B1, B2, and B3 on a conic, and they can be anywhere you want, then Pascal, as a teenager, observed the following remarkable fact. It's often called the most famous theorem ever proved by a teenager. Pascal's theorem says that if you connect the A1, B2, and the A2, B1 to get a point, and you connect the 1s and 3s to get a point, and you connect the 2s and 3s, A2, B3, with B2, A3 to get a point, then those 3 points that you've created are going to be collinear. Now, this has has many unpleasant consequences, but one of them is that if you know 5 points, let's say you know these ones, and you want to actually physically construct the conic that passes through those 5 points, then what you can do is you can consider one of these lines to be variable. Let's say perhaps this one here. So we'll consider this line to be variable but fixed through A. And we want to sort of figure out where can B3 be. Well, so if these points are known, then A1, A2, A3, B1, B2, B3 are known, B1, B2 are known. Then this point, which is the intersection of these 2 lines, is known, so we'll color that. And this line is known. And if we're agreeing that this line is fixed, and so therefore known, then we know this point. And having these 2 points, that means that we now know this line here. And having that line, and also we know this point and this point, so we also know this line, so we know this point. And so now we know this point, and we've said that we know this point, so now, ta-da, we've gotten the B3. And so as this line rotates around, say, then this B3 will trace out the conic. Another important consequence in the same kind of direction is what happens if we have 5 points, A1, A2, A3, B1, and B2. And let's say we think of the third B point as being equal to say, A2. What does Pascal's theorem tell us in that case? Well, let's go through it. So A1, B2, we're supposed to connect A1, B2 and A2, B1 to get one of our middle points. We're connecting A1, B3 and B1, A3 to get another one of those middle points. It'll be up here now. And we're connecting A2, B3. A2, B3 we don't know because those 2 points are the same. We don't know that one. But A2, B3 and A3, B2, A3, B2 we know. So A3, B2 we know.
That's A2, B2.
Sorry?
That's A2, B2.
Oh, that's A2, B2, you're right. Thank you. Let's get rid of that one. I said A3, B2, we need this line here. Okay, so how can we use Pascal's theorem in this situation? Well, Pascal's theorem says that these 3 points are going to be collinear. Well, we already know 2 of them, so we know that the line that they're going to form. And we know that that third intersection point has to lie on that line. Well, we know one of the points, one of the lines, it's A2, B3. So wherever that line meets our central line is going to be another one of our 3 points along the middle. And then having that one, we can now deduce that A2, B3, the line A2, B3, must be this one. It must go from here to here. That's the line A2, B3. What that really is the tangent to the conic at the point A2. Right? So this is just a construction of the tangent to this conic at a point. In modern mathematics, we like to say things like, oh, consider a curve C, consider a point P on the curve, and consider the tangent to the curve C at the point P. Yeah, we can say that, but what does it actually mean? So 17th, 18th century mathematicians were aware that you really want to give a construction for a line. If you're talking about a tangent, you should give a construction for a line. And this is exactly that. It's a construction of a tangent, which does not require any infinite processes. It's a direct construction. Okay, so now we have the preliminaries. So I can now start on the sort of Euclidean geometry. So we're going to move to classical Euclidean geometry, but rather of a modern kind. And I want to talk about triangle geometry, which has seen a huge explosion of development in the last few decades. So now it's almost certainly the case that we know more about a triangle than we know about anything else in the universe. We know much more about a triangle. Whatever's in second place is in a distant second place. And largely that's due to the efforts of Clark Kimberling. And in organizing what do we know about triangle centers into his Encyclopedia of Triangle Centers. And it's in that context I want to talk about Schiffler points now. So I have to remind you, first of all, that if you have a triangle, so when we're talking about triangle centers, it goes back to the ancient Greeks. There are 3 classical triangle centers that you'll all know. If you take the midpoints of the sides and you join them to get medians, then we're getting the centroid of the triangle. If we take perpendicular bisectors, then we're getting the centroid, the circumcenter of the triangle, which is the center of the circle that passes through them, 3 points. And if we take the altitudes, they will meet at the orthocenter. Let's make them all big. Okay, and then the beautiful fact that was somehow remarkably left to Euler to figure out or discover was that these 3 points always lie on a line called the Euler line of the triangle. I guess the most famous line of triangle geometry. Okay, so now in 1985, Kurt Schiffler introduced what's now called the Schiffler point, which is quite interesting. And it's actually number 21 on Clark Kimberling's encyclopedia. It's, which means that it's reasonably important. So the story is this, that if you have a triangle and you consider the other classical triangle point, which is the incenter. So the incenter is what you get when you take bisectors, angle bisectors, and they meet at a point which is the center of the circle that's inscribed in the sides of the triangle. So that's the incenter. And let's say the triangle is A1, A2, A3. Then he discovered that the triangles A1, A2I, and A1, A3I, and A2, A3I have Euler lines which are concurrent, namely at S. So each of these individual triangles has an Euler line. So we have 3 Euler lines. Okay, I won't bother trying to figure out where they are. Maybe that's one of them, maybe that's another one, maybe that's another one. And those 3 Euler lines will meet at the Schiffler point. Yeah, so then there's a kind of a degeneracy and there's no well-defined Euler line. And moreover, the Euler line, the Schiffler point lies on the Euler line. Okay, that's great. But then in a few decades later, we got some more insight into the Schiffler point due to the work of 2 people who have the same last names, Emelyanov T and Emelyanov L. So Lev and Tatiana Emelyanov discovered this alternate way of thinking about the Schiffler point. It was around 2003. Okay, so here's their description of things. So there's the angle bisectors which meet at I, and let's call I now I0 because it's actually only one of 4 incenters. These angle bisectors, if you actually sort of look at them large scale, there's actually 2 angle bisectors at each vertex. The other 2 are perpendicular to the original ones. And these will meet at 3 other points, which are often called X-centers, but I prefer to think of them as just other kinds of incenters. So that's I0, we'll call this one I1, and I2, and I3. Okay, what's the Emelyanov construction? It's quite nice, but it also involves the circumcenter. So the circumcenter, we have to find the point which is the center of the triangle, so perpendicular bisector. Let's say that's the circumcenter of the original triangle. Yeah, the original triangle. Okay, so they said, let's do the following. Let's connect each one of these with the circumcenter, forming a line. And we'll note that once we've chosen one particular, we're going to do something for these 3. We're going to ignore I0 partially and just use I1, I2, I3. But once we've chosen I0 as kind of specified, then each one of these bisectors naturally allows us to identify one of these incenters with one of the sides. So if that's I1, then sort of consistent labeling would be A1 over here and A3 over here and A2 over here, I guess. Okay, so what we're going to do is we're going to take this line joining I2 and see where it meets the line L2. the line that corresponds to A2, which is the opposite line, which is this point here. And we'll join I1 with C and see where it meets the corresponding line, which is this one here. And we're going to join I3 with C and see where it meets the corresponding line. And then it turns out that these 3 points are perspective with the original triangle, and the point of perspectivity is the Schiffler point. So what does that mean? So that means now if I connect, let's say, purple. If I connect A1 with the opposite point, well, it's not much different, but anyway, and A3 with the opposite point, and A2 with the opposite point, then boom, there is the Schiffler point. Okay, so now I want to tell you about some of the observations that Nguyen and I have made. So the first fact is that both the Schiffler and the Emelyanov constructions generalize from I0 to I1, I2, and I3, giving altogether 4 Schiffler points. Let's call them S0, S1, S2, S3, all on the Euler line. So for example, if we had just done the original Schiffler construction, but we hadn't used the original incenter, but we had used one of the other incenters, then the 3 Euler lines would still meet at a point. That would be another Schiffler point, and it would still lie on the Euler line. And on the other hand, if we did the Emelyanov construction by not starting sort of with I0 and excluding I0, but starting with I1 and excluding it, then the same procedure would generate that same Schiffler point that we got in that situation. So we get actually 4 Schiffler points on the Euler line for a general triangle. But then we start at some point to realize that the situation is in fact much, much more general than that. And that in fact, once one looks at it much more generally, we see a much wider and perhaps more interesting story. So it turns out that if you start with a triangle, using the incenters is not important. What's important is that these 4 points that you have are a standard quadrangle with respect to the triangle. In this case, they are, because the lines joining them pass through the vertices. But we can actually replace I0, I1, I2, I3, I4 with an arbitrary standard quadrangle with respect to the original triangle. And it turns out not to be important to use the circumcenter. One can use, in fact, any point in the plane, and the Emelyanov construction will still work. So to explain that, let me actually kind of do it in a much more general situation. So I'm going to just choose 4 points. P0, P1, P2, and P3. I'm going to kind of mimic the Emelyanov construction. And okay, so which is what? But I need the 4th point. The 5th point will be, let's say, x. So maybe we'll choose some point x. So let's see if I can do it in this case here. Okay, so we're interested in getting 4 points. P0, I should start with. P0, P1, P2, P3. So let's start by, there's going to be 4 of them, so I'm going to start with, say, the one associated to P0. So what I have to do is I have to, first of all, create the diagonal triangle associated with this thing. Maybe I use a different color. Okay. It's not very good, but let's see if we can find the diagonal triangle. So there's one diagonal point there. There's going to be another diagonal point up there, and another one there. And let me just try to draw it by hand. Forgive me if I'm not very accurate. Okay, so there's the diagonal triangle of the original 4 points, P0, P1, P2, and P3. So what do we have to do for this Emelianov construction? Well, we forget about P0, and but we use P0 to identify these 3 with sides of the triangle. So if this is side, we're using P0, so that will identify this with that one. So this is sort of line 1, and we're going to identify this one with that one. So this is sort of line 2, and this one with this one, meaning that this is line 3. That line there is line 3. Okay, so what's the construction? So we join X with P1 and see where it meets line L1. There. We join X with P2 and see where it meets line 2. And we join X with P3 and see where it meets line L3, I guess there. And then we observe or find out this is corresponding to the, it's a perspectivity. So if that's, this was L1, I guess that would be A1, and this would be A3, and that would be A2. Okay, so we have to just join corresponding points. This one's on this one, so we have to join this one with here. This one's on that one, so we have to join it with here. And that one there, yes, that one is on that line, so we have to join it with that. All right, not too bad. That is the Schiffler point, S, that we would call S0. Okay, and now I want to tell you what's really going on here. Okay, in fact, I could have just eyeballed where S0 is. I don't actually even have to know the details of this construction because of something else that we found out, that these generalized Schiffler points are the meets of tangents to the conic determined by our 5 points, P0, P1, P2, P3, and X. P0, P1, P2, P3, and X. Are meets of tangents to the conic, yes. So what actually happens, let me draw a picture and I will clarify. So these are the 5 points, P1, P2, P3, P0, and X are 5 points, so they determine a conic. That's a conic. That conic has tangents. The tangent at X, here's the 5 points. Let's make it bigger. The tangent at X is this one here. The tangent at P0 is this one here. And what we're getting here, this S, is exactly just the meet of the tangent. It's the tangent at X meeting with the tangent at P0. And so these generalized Schiffler points are just points on the tangent. The generalized Euler lines are tangents to the conic determined by the original 5 points. There's complete symmetry between the P's and the X's. It doesn't appear that way, but in fact, they really are playing a completely symmetrical role. the p zeros and x. Those are 5 points that determine a conic, and it's the tangents to those conics that determine the Scheffler points. So this gives us, of course, new theorems about the classical situation, which is now a very special case. But because we spent a lot of time thinking about this situation, we gained some additional insights, which is actually the main thing I want to tell you about. Okay, so for that I'm just going to show you some pictures. Maybe I'll go over here. Okay, so now we're just studying 5 points in the plane and the conic through them. Very general kind of thing. So I'm drawing the conic to be the circle, and the 5 points are 0, 1, 2, 3, and 4. Those 5 points determine 5 tangent lines. This is completely special about 5 points, because that conic has tangents at those 5 points, and we know how to get those tangents using the Pascal theorem. So we have these blue lines are the tangents to these 5 points on the conic. And now this gives us a bunch of secondary points. It gives us, so there's meets of tangent lines. So this is like the meet of the tangent line at 3 and at 0. And also we have the joins of the points themselves. So the points like give you diagonal lines. Be 5 choose 2 diagonal lines. And there will be 5 choose 2 such meets of tangents. And once you have the meets of tangents and the diagonal lines, you can take intersections of diagonal lines, giving you these little blue points. And you can take joins of these, what I call hexagonal points, or these meets of tangent lines. So I've kind of introduced some terminology, for example. So this is the point 1, 4 square brackets means point, and round brackets means line. So this is the meet of the tangent at 1 and at 4. And the line that passes through 1, 4 and 0, 3, we can write that line or label it as 0, 3, 1, 4. And correspondingly, a diagonal line, like let's say this line here, passing through the points 0, 3, we could call that the line 0, 3 with round brackets. And then the meets of 2 of those, say the meet of this one and this one, would be given by 0, 3, 1, 4 with round brackets. So it's just a bookkeeping to keep track of diagonal lines and their meets, and tangent meets and their joins. Now there's a well-known theorem in this context, which is, maybe I can say it here. So have a look at this picture here. The theorem is that if you look at this, okay, this point here, I've got it labeled here, 0, 3, 1, 4. Okay, so it's the meet of this diagonal line 0, 3 and the diagonal line 1, 4. It is also it is lying on the line. So let's say I'll write here 0, 3, 1, 4. This is a theorem which is well known, classical kind of theorem. So I'll just illustrate it in an example. That the point 0, 3, 1, 4 lies on the lines 0, 1, 3, 4 and 0, 4, 1, 3. Let's see if we can see that. The line 0, 4, 1, 3, this one over here, is the line from here to here. And you can see that this line actually does pass through that point. And the other one, 0, 1, 3, 4, there's 3, 4, there's 0, 1, and the line 0, 1, 3, 4 is that one there. And you can see that it actually passes through there. So there's some lovely incidence already just in this basic triangle, or in this basic configuration with 5 points. Okay, so now to connect everything to the original configuration of this twisted icosahedron. Where does the twisted icosahedron come from? Well, so it turns out that if you look at all these points, not just the ones that I've drawn there, but all of them, that there's some additional beautiful conics that arise. In fact, there's 12 additional beautiful conics that arise that are contained in this picture kind of implicitly, and how does that go about? So let's say we take a particular example, and let me illustrate it. So this is dihedral conics. Okay, suppose we take a dihedral order of the kind that we originally were considering. Let's say A, which is 0, 1, 4, 3, 2. Then associated to this, if we circle one of the entries, say that one there, then the other 4 points give us, there's an adjacent pair of 1, 4, 3, 2. So you really should think about this as being 0, 1, 4, 3, 2. And if I sort of remove that one, then we have an adjacency here and an adjacency here, giving us this point 1, 4, 3, 2. And we have a non-adjacency between these two and between these two. So a non-adjacency will record with 1, 3, 2, 4. So we can do that 5 times, 1 for each one of these entries. So we'll get 5 such blocks. And then the claim is that the conic through the top 5 points is tangent at those points to the bottom 5 lines. So any 5 points, of course, determine a conic, but now we're getting conics which are actually have 10, that satisfy 10 conditions. So namely, you choose one of these things here and you get, maybe this is the relevant picture here. Let's look at here. So on this picture here, I've shown you in green one of these dihedral conics. This is the dihedral conic, which is actually C of D. It's associated to this particular dihedral order. And so, for example, if we remove 0, then 1, 4, 2, 3 should be one of the points on here. 1, 4, 2, 3, there it is there. And the associated sort of adjacent pairing is 1, 2, 3, 4. That means that if we're interested in the tangent to this conic at this point, it should be the thing that goes through 1, 2, and let's say 1, 2, and 3, 4. So here's 3, 4. Where's 1, 2? There's 1, there's 2. 1, 2 will be up here. Allow me to do that. 1, 2. So if you join 3, 4, and 1, 2, you will get the tangent to the conic at that point. So each dihedral ordering gives us a conic with where we have control of the 5 points and the tangents at those points, purely combinatorial in a very simple way through the configuration of the dihedral order. And then these 12 conics fit together in terms of an adjacency. So then this graph has an interpretation in terms of the relationship between these 12 conics. And an adjacency here corresponds to, well, you can see on these pictures that I that you have out there, you will see some situation where you have two conics meeting like this. Oh, that's not good. And they're meeting in two diagonal points, and they're also tangent with respect to these hexagonal lines that are dotted. So that's a very strong kind of adjacency there. They're agreeing at sort of in four points with respect to this structure that comes from the original 5 points. Whereas the points which are of distance 2 in the graph that are not connected by a bond but are only of distance 2, they correspond to the things on the picture where you have two conics which are adjacent in that way, and that they share a tangent. You'll be able to see some of those. That's the distance 2 interpretation. And distance 3, which is going from a point to an opposite, is where the two conics don't have any intersection. So this dihedral picture is a kind of a canonical kind of manifestation of this graph, which is very much like an icosahedron. Its symmetry group is S5, and I think naturally somehow connects with the projective geometry of 5 points. Thank you for listening.